Well, welcome to AP Calculus. I am Mr. Wixer, and I look forward to getting to meet you in the next couple days. This is not how I hoped to begin the year, with you at home and me at school with other students. Um, but until we actually meet this coming Thursday, because our time really is limited to try to get through this entire course, I am going to need you to start doing a little bit of work. But before you start getting into the beginnings of calculus, I figured it would be worth our spending a little bit of time talking about what exactly calculus is. This course is going to be different than the other math courses you've taken in high school because they've largely focused on taking tools you've already had and just sort of building on them. Algebra 2 built on ideas you already had from Algebra 1, just pushed them a little bit further. Pre-calculus took tools from Algebra 2 and pushed those a little bit further and added in some trig. Calculus is a different story though. Calculus will be about using all those things you've already learned about truly as tools to understand really just four big ideas. We are going to spend an entire year on just these four ideas. We're going to talk about the limit, and actually you'll start doing some work with that in just a little bit. The derivative, the antiderivative, also sometimes called the integral, and the definite integral. And truly, these four things will take us through the entire course. Let's take a look at them a little bit. The limit, which again will make a little more sense when you start looking at some videos in a little bit on that. But the idea of a limit is what happens when we can't plug something into a function, but can talk about plugging in something close. This function over here that you see, that x squared minus 4 over x minus 2, you are not allowed to plug 2 into that function, because if you did, you get a 0 on the top and a 0 on the bottom. But you can plug in things that are close to 2. What if we plugged in 2.1 or 2.01 or 2.0001 and started to get a sense of what was happening with that function? This is the idea of a limit. This will make a lot more sense once you start getting into those other videos for today. In about 2 or 3 weeks, we'll start talking about the second big idea, the derivative, which is really just a fancy word for slope. You know how to find the slope of a line, y is over run, y2 minus y1 over x2 minus x1, but here we're going to talk about finding the slope of a curve. I'm not totally sure how to do that right now, but those symbols that you see on the bottom, that f prime of 2 and f prime of negative 2, that's our fancy way of asking you to find the slope of the curve at those x values. And again, not really sure how to do that right now, but I know that at x equals 2, that graph of the parabola looks like it'll have a positive slope. At x equals negative 2 looks like it'll have a negative slope. And we'll see how to use some tools of calculus to actually calculate the numerical value of that slope. The third idea we're going to look at is the idea of an antiderivative. This is the derivative in reverse. I tell you a slope, and you tell me a function that has that particular slope. For example, find a function that has a slope of 2, and this symbol that you see over here, this elongated s with a 2 inside, it is asking you that question. Find something with a slope of 2. And actually, you already know that. What has a slope of 2? How about y equals 2x? Actually, you know a couple functions. Maybe y equals 2x plus 4 or y equals 2x minus 5. Actually, there are going to be infinitely many functions with a slope of 2. Our third idea is the idea of a definite integral. And it uses the same name, integral, and the same symbol, that elongated s that you see, but it actually asks a very different idea. A definite integral is all about finding the area under a curve. For example, I want you to find the area under the parabola y equals x squared between the curve and the x-axis, starting from x equals 0 and going to x equals 2. Well, not really sure how to find the area under a curve right now, but we're going to see this is actually going to follow from the formula for area of a rectangle that you learned about in geometry, just with some enhancements to it that will let us find the area under any sort of curve. And those are the four things we're going to spend the entire year looking at. Now, all of those topics will approach from four different angles. We will look at things graphically, numerically, algebraically, and verbally. This isn't just me talking, this is also the College Board. This is a very big focus of the AP exam, being able to look at all of those topics from these 4 different approaches. Let me show you what these approaches mean. Graphically, can we look at a graph of a function and find a limit, a derivative, a definite integral? Numerically, can we figure these things out from tables of values? Can we find out a limit from a table of values, or a derivative, or a definite integral? Analytically, or algebraically, this is probably the approach you're most familiar with from previous math courses. Here's a formula. Can we find a limit? Here's a formula. Can we find a derivative, an integral, a definite integral? The final approach is the verbal approach. Can we talk about these things using clear and appropriate language and clear and appropriate notation? The language you use in this class and the notation you use will be a big deal, not just for me, but also for the AP exam and for math courses moving forward. Now, in addition to these 4 big topics with 4 approaches, there are many applications we're going to look at. And I want to give you just a small overview of those applications. I think that should do it. One idea is the idea of a function being continuous or differentiable. We're not going to worry about the differentiable part right now, but you learned what a continuous function is back in Algebra 1, Algebra 2. Can you trace out your function without picking up your pencil? Well, we need to give a formal definition for that. That's not really mathematical. Can you trace it without picking up your pencil? We'll see how limits can be used to give us an actual definition of what it means to be continuous. Next idea, the idea of a tangent line. Hopefully you remember from geometry that if something is tangent to something else, it just touches it. It doesn't cross it in 2 places. We want to find the equation of this line that is tangent to that parabola. Next idea, related rates. The radius of a balloon is increasing at a particular rate. I want to find how the volume of the balloon is increasing at a particular instant when the radius is fixed. How does one thing changing affect something else? Curve sketching. F of x equals x to the 4th minus 3x cubed plus 2x minus 3. We're going to see how some tools of calculus will let us figure out that the graph of that function looks something like this. Previously, you would have only been able to do that using the graphing calculator, but we'll figure out where this is increasing and decreasing, where it has a maximum and a minimum and another minimum and things like that, and get a pretty good sketch of some random function. Optimization. We want to find the maximum possible area, and you did this last year, and probably in Algebra 2 as well, but you did this by using the graphing calculator and finding the maximum that way. We're going to see the actual mathematical way to find a maximum or a minimum. Motion problems. Well, first of all, hopefully you saw that little particle move back and forth on the bottom of your screen. If you're taking physics this year, you will definitely see some overlap between that class and this class. We want to analyze the motion of that particle that was moving back and forth. What's its velocity? When exactly did it change direction? What's the total distances traveled? And we can do that from our formula and those tools of calculus that we'll develop. Net change. If I have some formula that tells us the rate that water is flowing out of somewhere, I can figure out how much total water is pumped out using some ideas from calculus. Functions defined by integrals. We're not going to talk too much about this right now, but I have some crazy looking formula up there with an f and a g, and somehow this graph is connected to it. Don't worry, when we actually get to the stuff, this is not going to be big. But we'll look at functions defined by these crazy formulas and graphs at the same time and try to analyze them. Differential equations, another thing we're not going to worry too much about right now. I've got a crazy looking equation like that thing. Somehow this picture is going to help me solve it later on in the year. That'll probably be about January or February. Average value of a function. You know how to find the average of a bunch of numbers. You add them up, divide by the number of numbers you have. But to find the average value of a function, well, I want to add up all the heights of this function, but there are infinitely many of them, so that's not really going to work. But we can use some tools of calculus to somehow add them up and come up with our average height. Area. We already saw that definite integrals can find the area under a curve, but we can also do something to find the area between two curves, like what you're seeing over here. And finally, volume. I'm going to give you a region, like that. We're going to spin it around the x-axis. It's going to look something like this. And somehow, we're going to try to find the volume of that shape. And actually, that's kind of where we're going to end by the end of this course. Just a quick overview. This is where we will travel throughout the course of the year. You are going to start your study right now by starting to get into the details of limits. So that will be in the next video. Looking forward to meeting you in a couple days.